All right, for our second speaker for the Turbo Talks, I'd like to introduce Jason Raber with Function Rerouting from Kernel Land with Hades. Thank you, Jason.
Okay, well, she read my first slide, so I'll move on.
I was trying to help you out.
So here's kind of what I'm going to talk about. 20 minutes, I'm going to cook through at least the output and overview, and I want to take you through actually some of the source code and then where to get it. Okay, so what is it and why am I creating this thing? You know, for what I do for my job, I do a lot of reverse engineering and red teaming. And what I found is, you know, walking through a debugger is kind of a slow process. So what I like to use is either detours or WinAPI override, or, you know, these are kind of profilers that will hook DLLs, or you can modify them to actually hook the actual internals of functions. Okay, and so then what you get out of that is something a little more readable instead of a run trace from a debugger. Again, I found that it's much faster in reverse engineering. But a lot of the stuff that I look at is got protections. Okay, and so normally, you know, the detours, the trace API, and WinAPI override are pretty stealthy and they work real well. The problem is the way they work is they need to load a DLL in the process space when it's running. So what happened was I was looking at some malware, and the malware was not allowing any kind of unauthorized DLLs to be loaded in the process space. So this is where the motivation came for me. I was kind of like, well, okay, well, how do I do the same thing that detours and WinAPI overrides is doing without, you know, loading a DLL? So, you know, in a lot of reverse engineering, when you understand how to pass control from user land to kernel land, you use NTDLL as kind of like the gateway, right? It does a sysenter or an N2E or something along those lines. But it sets up, you know, the stack frame and passes it along, right? So I said, well, maybe I can write a driver that will allow me to do that. Let's see, and that's kind of really the motivation. It kind of worked that way. Okay, so I've got two different outputs, as you can see over here. This is kind of what you normally would see from a profiler, but I've got a more verbose mode. So if you download the source code, and, you know, because I don't really, this is the way I debug drivers, is with a lot of debug prints. But you can see here, here's the program. It's very simple. It's just a hello world program. It runs. And you can see where I'm hooking foo2, okay? And in this case, the program just prints out the parameter, okay? But you can see up here that foo2 is called 4 times, and I catch all the parameters and I print them out. In addition, it also does foo4, which, you know, the output here is just 3, but if you disassemble it and look at it, it takes 2 parameters, adds them together, and prints it out. So again, very simple example. Okay, so now let me take you through kind of the high-level view of how the product works, and then we'll take you through the source code. Okay, so down at the kernel, I need some sort of toehold, okay, that allows me to pass or catch control when I pass it from user land down into the kernel, right? So when I load the driver for the first time, I hook load driver. Now you can, like I said, when you download the source code, you can use any syscall that you want to use. I just picked this one because it's not getting called a lot. Okay, but I'm not going to go through too much on how to hook drivers. You can Google that, or hook syscalls. It's pretty beat to death on how to do that. The next step that I do is there's an area of memory between user land and kernel land called shared user data. Okay, and the kernel or operating systems will use this. Windows will. It used to actually throw code there, but with later versions they just use data. But NTDLL will use this area of passing control from user land to kernel land. So what I said was, well, I'll use this as kind of my trampoline to when a process is loaded in memory to jump to. So I'll talk more about what the trampoline and what those instructions are in a minute. Okay, so then the third step that happens, okay, is there's basically a callback, okay, a register callback in the driver that when the target process gets loaded in memory, I get invoked, okay? But the key here is that the Windows loader has loaded the process in memory, but it hasn't executed the original entry point, okay? So it's just sitting there in memory, and I got a chance to go do something. And so then what the driver will do is actually go to the functions that I want hooked and jam a jump right in the beginning of the functions, okay? So in the case of foo2, foo4, or however many functions you want, there's going to be a whole bunch of different jumps that get injected before original entry point is executed. So So once that happens, the driver just lets go and says, okay, go do your thing. All right? So the window says, okay, great. The instruction pointer starts at original entry point. It works its way down, and it finally hits your jump. And obviously, I hope you know where that goes, right? And like I said, this is the novel piece, right, is that we're not using a DLL to be loaded in the process space, because that is a protection or an anti-debugging technique that they look for, or anti-tamper. Okay? So when that jump happens, it jumps down to that trampoline space, and you could see the instructions here where I'm basically saving the stack context, saving the flags, and I need an identifier. The reason I need an identifier is because I have multiple hooks. Let's say we have 100 different hooks. Well, I need to know where I came from, right? So now I have to pass control down to the driver so I can get control, right? And that's where you'll see this jump to the handler. Again, imagine this is duplicated, maybe 100 different times, depending on how many functions you have hooked. This is only one time. Is we load an identifier 61, and you can disassemble NTDLL, and you can see all the different identifiers for all the different syscalls, right? And for load driver, that's 61. Saves off the stack and does a sysenter. All right. So what happens after the sysenter? Well, because I loaded the identifier for the loading of the driver, and I have that guy hooked, after the kernel does its thing, it's going to pass control to my hooked load driver, right? So at that moment, now I can print, we're laughing, right? Because now I can print out the registers, I can print out the parameters, print out the function. You can do man in the middle and change the data in transit, or not even do the call if you wanted to, right? But then the last thing I want to do, obviously, is because I want to keep my hooks in place, I want to restore the context, and here's the kind of the trickier part, right? Is up in foo2 or in all the different functions, I had to steal all those, 5 bytes or 8 bytes or however many bytes, depending if there's a bleed over with my jump. I had to steal those and emit them down into the actual driver. So when the instruction pointer is done restoring the context, I actually need to execute them. So things you got to be aware of if you download it and start playing with it. If you reroute some functions and they have control flow like a return or a jump or a call, you're going to hose yourself, right? So, but generally, if you're hooking functions, they're going to be stack, frame, setup, those types of things. So it's really instructions that are not going to hurt you if they're executed down in the kernel. All right. And so, in this particular case, I stole 5 bytes. So the next thing that I want to do, I want to leave my jump in place, right? Because foo2, as you saw, was called 4 times, or you might be in a loop, who knows? But I want to leave it in place, right? So I want to jump as the offset of up to 6 or whatever, so I pass over my original jump. So that's kind of how it works on a high level. Let me talk a little bit how the source code, or at least points that I want to make, so that hopefully you download this presentation, and if you're looking at the source code, it'll make more sense. Again, the hooking of system calls, you can look that up, but basically it's, there's a table. I'm just swapping some pointers, as you can see here, down where the original load driver is. So I can call the original one if I want to. The next thing I want to do is, call this PS set load image notify routine, which is a callback. It takes a function pointer, okay, and basically in that function pointer, I'm just setting up whatever that target process, when it gets loaded, please, I want it to be called before the original entry point starts executing. All right, so now that our process has been loaded and our callback has been invoked, we want to go ahead and start setting up the hooks, right? So remember I was talking about like foo4 took 2 parameters and foo2 took 1 parameter. So basically you're setting up a function pointer, okay, with here's your parameter, int, and here's the virtual address. And same thing with foo4 in this particular case, it takes 2 parameters, and so we set that guy up, and then we call route function, which is over here. And remember, the only other point I want to make here is it's fairly simple code, but with the offset, remember we're generating the jumps in the driver, at load time of the process. So when those jumps come down to the trampoline, they have to be offsetted for each particular jump because of the trampoline area. You can't just start at the beginning, right? And then we save off the IDs down here of the, as we're pushing in the identifier right here and the actual destination, we want to save those off. So when I get control, I need to know which hook function to go call to print out the parameters and do whatever I want to do, right? Okay, so now that our jump has been executed, we're down to the trampoline. We go ahead and save off the stack, okay, and then we invoke the sysenter, which then, as you can see over here, this is where we got the hooked load driver, where I'm saving off the stack, and then I call handle the hook calls. So then basically I can figure out which identifier I passed up right here, right? And as you can see here, where I'm pushing the registers, the flags, and the identifier. Identifier was the last thing to push on, so it's the last thing on the stack. So that's at the top. Again, my comments reflect that. And then down here in the get called call address, again, I'm just looking up the identifier to figure out which hooked function to call. And that's where we get here. So in this particular case, of this particular example of hooked 2 got called first, or got invoked first. So this guy gets executed. And again, it's really easy at that point because now we're just at the very beginning printing out, come on mouse, printing out our parameter. And again, this is kind of cool because at this particular point, if it's an anti-debugging function, for example, let's say maybe you want to take a debugger and you want to attach it, but your debugger is getting caught. Real simple example is debugger present, right? So in this particular case, if you've got that particular function hooked, you can just return 0 instead of true, right? So it allows you to do some powerful things there as well. And then the last thing, we want to restore the context and then, emit these instructions. You can hand code the assembly code or whatever, and you can write maybe some sort of plug into IdaPro that'll automatically generate this. This is just a kind of a proof of concept. Can I do it? And yeah, so it's kind of neat. And then obviously I had the offset before I push the flags because you don't want to add before messing with flags, and jump back. All right, so again, that took like 2 weeks to actually develop all that just to see if I could do it because kernel level debugging is really not all that great, or so fun. But then I thought, well, if I can do that, well, what if I could actually just make slight mods to this rerouting capability from the kernel and make it into a debugger, which I did. But again, I only probably spent like a day doing that. Okay, so it's very, very limited. It's a one-time breakpoint. And when so basically you hard code a particular address that you want to print out the registers or maybe even change the registers. You compile it into your driver and you load it. And it works off the same premise of the trampoline, of the shared user data, the callback, the register callback, all those types of things everything's the same. So as far as the actual source code, again, you can probably do this all from the command line, but I just wanted a proof of concept to see if it worked. But these 2 files you have to modify as the source code is now. Just change it from the data mining to breakpoint, and then hard code your BP1 to whatever address that you want. Like I said, it's limited to 1, but modify away, and you can make all kinds of make it unlimited breakpoints. And again, it's just like the rerouting stuff. I put a verbose mode versus the short, just because that's how I debug my drivers and stuff, how I steal the bytes and put it back, etc. In interest in time, these are just basically the 2 functions that really had to be written that's different than the original core of the rerouting code, right? So on how I add the actual breakpoint. And the other thing is, like I said, because it's a one-time breakpoint, remember for the function rerouting, I was leaving my jump in there because it could be called many times, right? For the one-time breakpoint, I just, as I take the bytes and steal them from the jump, I just throw them right back in. So in other words, when control comes and is passed down to the driver, first thing that I do is restore the context and restore the stolen bytes, print out the registers, and then jump back, right? So fairly simple. As you can see right here where it's doing the writing back of the memory, printing out the memory, and then jumping back. Okay, so here's where the source code is. I'll leave that up. I'd ask you is, if you download it and you make mods to it, push it back up there so we can all benefit. Are there any questions? Nothing? Driver development, yeah. Well, anyways, download the source code and have fun with it. It can be used, I think, fairly for. We use it, to get around a lot of anti-debugging types of tricks and anti-tamper. And I mean, the obvious thing is when you're using the rerouting capability, if the code has checksums in it, it's going to catch you in that regard. But it'll catch you with WinAPI or override or detours. So same there. But at least with the debugger too, it's a one-timer. So, I think there could be some interesting things from it, right? You could, in theory, reroute every single instruction as it's going through, and then you would get around all the checksums, right? So if you wanted to set a particular breakpoint at one area, you start rerouting from the entry point of the program, original entry point, and just keep replacing the bytes. If it goes through any checksum or anything like that, at least when it's executing, it's all back to pristine condition, right? And then you don't have the weight of the extra DLL trying to hide that. So, yes?
Do you have any concerns that this might be perverted and used to attack anti-copying measures that people are putting into their software?
Well, yeah, it could. It's a debugger, right? So it's you can use it as a debugger, and when we use it primarily for getting through malware quickly. So we've got an assortment of different tools that we develop ourselves, like this, or proof of concepts, and then turn it into something else. But again, if you're looking at malware for any length of time, it kind of gets old with all the anti-debugging and IDA and OLI and all that kind of stuff. Slogging through it kind of gets hard. So, but yeah, it does add a level of stealth, which makes it interesting, I think. So, anything else? Nope. Okay.